So rotation, rotation, rotation. Let's get into what rotation is and isn't. I'm going to admit right here that rotation actually applies to two things that I'm putting together and calling rotation. They're not both rotation. One is an orbit and the other is a spin. The Earth, as you may have heard, and hopefully you believe, the Earth goes around the sun. There's our year. The Earth also, as you may have heard, and some people believe, spins on its axis, and that causes the day, right? Yeah. Okay, so those are two different kinds of motion. One is you could describe as a point object rotating around a center, and the other is an object which is not a point rotating around its center. Hey, by the way, these slides are all posted. We're back to slide land where I've got things that you can download. So don't feel like you have to write every word. Okay, these are two different kinds of things that I'm conflating, but the same math for orbits applies to spins as well. So I'm going to talk about circular motion and rotation all put together, smushed together, and have different examples in the same phenomenon in different contexts. Be aware of that, right? Spinning and orbiting are different things, but they have the same structure underneath. Okay. I also want to note in the first point here, when an object moves along a circular arc, that's not even completely a necessarily complete circle. If you go out in your car and do donuts in the parking lot, one, don't. Two, that's a complete circle, sure. But the very same physics applies when you are simply turning from going straight down a road to turning left or right or whatever. You are changing your direction of motion from this way to that way. While you are in your turn, you are moving along a roughly circular arc. So the same physics that we're doing here applies to that, even though you're not going in a full rotation. Now, one of the big things thou shalt learn, is that there are two kinds of speed, or to be precise, velocity, in circular motion. There's the good old ordinary v. You know that. That's just distance over time, or to be more precise, displacement over time. I'm most often going to ignore the direction there, unless I don't. And then there's a new quantity. Oh, and I'm going to call him, to distinguish these clearly, I'm going to usually call him tangential speed. That is to say, you are moving along tangent lines along the edge of a circle, moving in the direction of a tangent line, the direction of a line that skims the circle. That is your speed in that direction. That's tangential speed. Our new speed, the speed of the angle, the angular speed, is called, oh, here's a big shocker, it's called angular speed. Very confusing terminology there. Please note, V has evolved. V has a Greek counterpart in angular land. X, V, A, T. Well, T stays the same, but X, V, and A from last time we did motion, you know, the first module, those are all ordinary English letters, well, Latin letters. Angular terms are going to be given Greek letters, and we're really only going to be focusing on one of these because I've cut the curriculum. But the angular speed, this is not the letter W, curly bottom, this is the Greek letter omega. This is lowercase omega. All right? Don't call it W, please. You could type it if you've got to type it. In a computer, you could type it as W. But it's not, I mean, the Greeks did lots for us. They were some really smart people. Why don't you use the right letter? It's called omega. Okay, so, as I said, velocity, distance over time, displacement over time. You know that, hopefully you know that, right? Pretty darn well. Our new term is angular speed, so let's go in and talk about him a smidge. Come on. Oh, right. No, sorry. One brief point about the nature of tangential speed, ordinary speed on a circular edge, is tangential speed is, defined as it always is, the distance traveled by an object divided by the time it takes to travel that distance. Hopefully point one on this slide is obvious. something you know. I want to emphasize that if you're moving around a circular arc, if you're moving along the path of a circle, where are you going? What is the distance around a circle called? That's circumference. So muy importante, a very important formula that thou shalt remember is the circumference formula. Let's see how many of you remember circumference from geometry in high school. And when do you learn circumference? Middle school? Whatever. Type it into the Google form. Google question A. What is the formula for the circumference of a circle? Oh, and I have signed out. What? 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 Okay, I asked this for a reason. And that reason is it is not uncommon. Yep. I got about 2/3 of you. Muy importante. It is not pi. It is not pi r squared. It is not 2 pi. The formula for circumference, the distance around the circle is, write this down if you got it wrong, 2 pi r. 2 pi r. 2 pi r or 2 cake r? No, it's 2 pi r. Okay, so if you said pi r squared, what's that? What's pi r squared tell us? It's the area of a circle. That's important, that's good, that's great, but that's not necessary at all for this module. We'll use pi r squared, I think, maybe. I can't remember. Maybe next semester. Can't remember the lesson. Okay, so very important. The circumference around a circle, you will end up needing this to do some computations, is 2 pi times the radius of the circle. Hey, what's pi? 3.14-ish. 3 degrees, 3 digits is plenty to, three sig figs should be plenty to get you through. Or you've got a pi symbol on your calculator. Okay, so motion along a circular path lies on the circumference of a circle, and thou shalt know the formula for the circumference of a circle. I want to emphasize something about the nature of velocity on a circle, and that is if you go on a big circle versus go on a little circle, if you take the same amount of time, you'll go further along the circle. Or it's not, let me say it the way I said it here. To go the same around the circle, to keep up with a race car on the inner track of the circle, if you want to cover the same revolutions per second, you have to go faster the further you are from the center. An example, suppose you got 2 cars, maybe going around a racetrack. Why do NASCAR drivers jockey for the inside lane? Because they don't have to go as fast on the inside lane to take the turns. A race car in an outer lane has to be moving faster than on an inner lane to turn that 90 degrees. It is a bigger distance along the outer edge than it is along the inner edge. So there is a, in fact, direct relationship, directly proportional relationship between the size of the circumference and the size of the circle. Wait, hold on. Circumference equals 2 pi times r. Well, of course it's directly proportional, right? If the distance per time depends on the radius, the bigger radius has to go with the bigger circumference. It would have to go with the bigger speed. That should hopefully make a bunch of sense. Do you have an intuitive feeling for if you keep up with the same rotations per second, if the times are equal, you're trying to get around the same amount of circle, bigger circles, you would have to have bigger speeds? Okay, good. So that's an important point that you will need to think about throughout this. Now let's introduce angular speed properly. Angular speed is the speed of your angle. Oh, well, that's actually not that hard. Well, there are a couple of subtleties here. And a typo. Angular speed is, I define as the rate, that is to say, divided by time, the rate of change of angle. Angle is God, I hope everyone knows what an angle is. An angle is what was in England before 1066 came along. Hey, history joke. An angle is the inside wedge of how much an arc is. I don't know a better way to describe that. So if you've got some fraction, if you've got motion around, if you are changing your angle, you can take the amount of angle, and what did I say about rate? Rate always means divide that by the time taken. That's angular velocity, angle per time. I want to emphasize, by the way, a very common example that probably half of you have inside your cars is the tachometer on the right side of a car dashboard display. The RPMs meter. Who has an RPM meter? More than half of you. Okay, my car doesn't. The RPMs, that's angular velocity. Rotations is one way to measure angle. You go around 360 degrees, 2 pi radians, 1 rotation. We're not talking about a distance, we're talking about how much of a turn that's an angle. Rotations per minute, angle per unit of time. That's omega. That's what omega tells you. Okay, so, I like symbols, I like angles, I like equations. Let us define this idea precisely by saying that the angular velocity, I'm going to call it omega, as I did before, not W, is equal to how much the angle changes by, divide that by how much time it took to change that angle. Theta is the traditional symbol from geometry for angle. Delta theta tells you the change in angle. Delta t is, not surprisingly, I hope, change in time. So if you find out how much your angle has changed by, and find out how long it took to change by that, the amount of angular change divided by the amount of stopwatch time is the angular velocity. Okay, I want to emphasize here again, please write this down if you do not know this, if you guessed or misremembered. You're going to need this in a second. The amount of distance, the length of a string lying along the outside of a circle is the definition of the circumference of the circle. That's given by the formula 2 times pi times r, where pi is approximately 3.14. Now, this is a typo. There is no such thing as a negative speed. This should say angular velocity. I'm going to conflate them all the time. Most of the time here, I'm actually talking about angular velocity. Sorry. So, positive versus negative sign here no longer talks about up versus down because there is no up and down in a rotation. There is no left and right in the rotation. What we can assign for a rotation is that rotation going like a clock or opposite of a clock? And the mathematical convention for angles is the usual way in math class you start by teaching angles is you teach that this is what? This is along the x-axis is 0 degrees. And then the angle is 10 degrees, 20 degrees, 30 degrees, 40 degrees, 50, 90 degrees. Yeah, it increases as you go which direction? Is this clockwise or counter? Counterclockwise is the positive angular direction. So if the angle increases, omega, delta theta is positive, omega is positive, right? That is to say, angular velocity actually is positive if we are rotating, spinning, orbiting counterclockwise. Negative is obviously the opposite. Please beware, if you're used to looking at maps a lot, we often say 0 degrees is north, and then clockwise around the north direction is how we define positive, you go 0, 10, 20, 30, 40, whatever. That's not the math angle convention. So if you're used to looking at maps, be aware this is different. Clockwise is negative, counterclockwise is positive, x-axis is 0. Who looks at maps a lot and thinks about 0 as north? Oh, well, that makes my job simpler. Ready for a problem? Think you can do something with the things that I've taught you so far? There are only a couple of definitions, but all you got to do is stitch these together. Please, for the love of God, think about the meaning of these terms and do not guess whether to multiply, divide, or add, or whatever, okay? Here we go. I say I've got a carousel, which is also a merry-go-round. A horse on a carousel / merry-go-round is 4.2 meters from the axle, central axis. And I'm going to say it takes about, I'm guessing, I was imagining the one in Phoenix Zoo. I think it takes about 8 seconds to go around, about 0.13 revolutions in each second. An eighth of a. Okay, I challenge you to tell me the tangential speed, v, based on this information alone. Ready, set, go. This will be Google question B. No, there is not a equation that I have given you. You just plug into. You got to think about the meaning of these. Correct answers already. Ooh. You should also sanity check your answers, by the way. Think about how fast 1 meter per second is. 1 meter per second is like 2 miles an hour. If you're getting 300 meters per second, I don't think that the kids on the carousel are going the speed of a jet plane. You laugh, but y'all make this mistake. Everyone makes this sort of mistake. Sanity check it. How fast do they really go? Rev, by the way, means revolutions or full turns. Full circles made in each second. I also want to point out that revolutions per second is not quite angle per second. I have not told you omega yet. I have not told you how we measure omega yet. I am pleased. A lot of correcto answers real fast. I'm going to say 1 more minute. It's going better than expected. And time's up. I am pleased. Well, more than half of y'all were able to figure it out based not on plug and chug, but reasoning. Or at least that's my hope. That's how you came up with it. I want to walk you through my way of thinking about this because I'm going to introduce to you an important term along the way. By the way, the correct answer is about 3.43 meters per second. If you got this, give yourself a pat on the back, particularly if you got this by thinking logically about distances and times. Okay, so here's how I think about this. What is distance and what is time that you know of? You know a radius. Do you move along that radius line? Does the carousel horse go from the outside of the circle straight through the middle? Not unless somebody's in big trouble on the engineering team and the kid riding the carousel. Okay, so no, carousel does not go along the inside. The carousel horse goes around the outside. I am talking also, by the way, I know the path it goes, but I'm also giving you information about the time for one full orbit, one full revolution, one full cycle. So I think it makes sense to compare time for one circle here and time and distance in one circle. I start by calculating the circumference of the the circumference of the words. The circumference of the horse is what? 24 point what? 26? 26.4? 2 pi times 4.2. This is 2 pi r. 26.4 meters. That is the distance around, and I can say if I only knew the time around, I'd be done. Well, let's look at what I done give you. I gave you something relating to time and cycles. What is that? Does that tell you time, revolutions per second? No. Revolutions per second tells you the number of cycles that you get in 1 second. I want the number of seconds in one cycle. What is the relationship between those two fractions? If I told you the number of revolutions, x revolutions, actually I'm going to use the letter that we do traditionally use here. If I tell you that there are f revolutions in 1 second, how is that related? How is that? What is the relationship between that in t seconds for one revolution? What is the relationship between f and t there? Revs per sec, secs per rev. How could I get from f land to t land? Tell you what f and t stand for in a second. How do I get a fraction upside down? Huh? Yeah, yeah. T is the reciprocal of f. If I want to know the time for one cycle, and I give you the cycles in 1 unit of time, these are reciprocals of each other. So I think that it is important to be able to relate these to each other and say that the time is equal to 1 over this. I told you frequency, cycles per second is named frequency. I want you to find period, which is seconds per revolution. So what I do, how I think of this inside, is that I calculate the time to go once round. By the way, convention here, capital T is that particular time that means one revolution time. Lowercase t can be anything. But if you see me write a capital T here and I'm not talking about tension, then I'm talking about the time to go all the way around once. Hey, what's that? Someone with a calculator. 7 point something? What's 1 over 0.13? No. 6 point what? No, 1 divided by 0.1, 7.69. There we go. I know the distance I have gone. I know the time it took to go it to oh, for God's sake, to go it. I say that tangential speed is nothing but distance divided by time. Oh, I only have actually 2 sig figs here. I should say 3.4 meters per second. Again, if you said 3.43, I'm not going to take off points. Okay. Now, that's good and all, but I want to learn 2 more things from it. One is what I told you a second ago, the words. And the second is to look into the mathematics behind this fraction, and that'll motivate the next slide. Okay. So, first off, this is the answer. Are you okay with the answer? For reals? Question me. What do you mean take the? Because you don't yet know the equation relating radius and frequency. How I expect you to reason about it at this point, we are going to get an equation for this in a minute, but what I want you to think about and how I expect and predict that you can and should reason about this is to think about what is distance, what is time. Distance where? Hopefully you said around the circle, not across the circle. And time for what? I tell you about how many revolutions you get in 1 second. I think it is the straightest forward way is to do that is to think about the seconds in 1 revolution. That formula you just said works. We're going to go into that in a second. She had a question. She is the whiteboard. No. She is someone on Zoom. And I saw a question on the far left of the room too. Okay, another question. Would you be able to multiply? Yes. But Mitzi, again, I challenge you to say that's what he said. I challenge you to say, why would you multiply that by that? Well, actually, let me ask. Fernando and or Mitzi, why do you multiply those 2 quantities together? What is the meaning when you do that? The portion of the circumference is 26. Oh, all right. I'll take it. That's another reasonable way to reason about it. Sure, I'll take it. I'm still going to say, please do walk through this process, because this is how I'm also taking a step to my next concept that I've got to introduce. But yes, you're right. That absolutely makes sense. Good. Question. Great. So yes, I don't personally think about it that way, and there's a reason why we're talking about it this way. But yes, if you did that and reasoned about it that way, I'll take that. Okay, now let's talk about the puzzle pieces in here. I say the 0.13 revolutions per second. What does that mean? It tells you how many times something happens in 1 unit of time. This is period. Frequency, sorry, frequency. This is frequency. Frequency is going to pop up multiple times in this class and next semester and in some of your other classes. Frequency, we often call F. So there are other letters used. Sometimes you will say nu, which looks like a V, measured in hertz. Oh, it hurts. One hertz is the same thing as 1 time per second. Hertz is a convenience unit. HZ, hertz, capital H, HZ is the same thing as inverse seconds. And you will sometimes see frequencies written as 1 over S. I won't do that, I don't think, rarely. So I'm more likely to write rev per S, rev per sec, or whatever. But you must know for this, here's a defined term here, the idea of a revolution, a number of cycles, a number of revolution, a number of times per second that something happens is the meaning of frequency. And you will see me write this as HZ, is its accepted unit. You feel okay about frequency? Period means, oh, and to be parallel, I should measures is the time needed, that's a silly word, for one cycle. For one cycle of something to happen. Period and frequency apply to a million different scenarios. For circular motion, uniform circular motion, I'm going to say frequency is the number of times you complete an orbit per unit time. Period is the number of seconds it takes to complete an orbit, but this appears in many different contexts, so beware. Think about the meaning, not just tying it to a particular angle thing. Hey, what's tempo? Any musicians in here? What does tempo tell you? How what? The speed of the music? How many meters per second it goes? Beats. What's a beat? What's a beat measured in? No, a beat isn't minutes. A beat is one time you do something, right? If you hit the drum to make a beat, that's not a meters thing. Yeah, I guess you could have a volume thing, but no, beats per minute is frequency. Tempo is frequency. And instead of writing andante, allegro, despacio, wait, I forgot one. Instead of writing those Italian words, we could very well specify frequency in hertz. But a hertz measures the number of times something that happens, and not necessarily a circle, not necessarily circular motion here. Now, if the concept of frequency, times per second, and the concept of period, seconds per occasion, makes sense, here is a defining core central key equation. Period is inverse frequency. I'm going to make bullet points here, maybe. Thou shalt know period is inverse frequency. And what would happen if you solve for F? Let's do this. Google form. Everybody solve for F. Tell me if F in terms of T. Google form C. Solve for F. F equals what? Show me you can algebra or arithmetic. F equals 1 over F. What? Solve for F in terms of T. Yes, I know it's frequency. I want you to give me an equation. No, I know it's 0.13 in this case. I want you to give me an equation. How is F related to T? I just told you T in terms of F. Please solve for f in terms of t. Okay, and again, you should solve for f. There are several people telling me true equations, but I am looking for an equation f in terms of t. Start here in algebra until you have solved for the variable. Solving for a one variable, you can do it. Okay, time's up. Here's how to solve for a variable. I see f downstairs. I don't want him downstairs. Fractions are terrifying. Let's eliminate the fraction. How do we eliminate a fraction? I eliminate a fraction by multiplying by its denominator. If I do so, then I get the downstairs vanishes, and I get t times f equals 1. Well, now I've got no fractions left, thank God, but I've got t is attached to f. I don't want tf, I want f. T is attached with multiplication, divide by it, and you get the final answer, f is 1 over t. F is 1 over t, t is 1 over f. They are reciprocals of each other. Seconds per cycle, cycles per second, reciprocal, reciprocal. Questions about period and frequency? Great! Now there's one more thing here that I want to dive into, and I should have left a blank slide. Before we hit the next thing, I want to motivate. I want to motivate where this next thing is coming from. If we write what we just did as an equation instead of just an equation instead of just multiplying and then dividing numbers, what did we do? We said that velocity equals 2 pi times radius over, I thought of it as inverse frequency. 1 over an inverse is equivalently equal to 2 pi times frequency times radius. Or 2 pi RF if you like, whatever. Algebraic rearrangement is legal. What does F tell you again? The number of times per second something happens. What does R tell you? The width of the circle? There is a very important term I'm about to give you, which tells me not the cycles per second, but a very related term to full rotations. What is the relationship between full rotations and radius lengths around the circle? Radius lengths are also called radians. Has anyone ever heard of the radian? Yeah? 1 radian, 57.3 degrees, if memory serves. 1 radian is defined by the idea that there are 2 pi of them all the way around a circle. So if I multiply 2 pi, what this really is, I can interpret this idea as 2 pi is not just 2 pi r as circumference. I can say 2 pi is a conversion factor. 2 pi is the radians per circle times circles per second times radius. What's radians per second? Look at your notes. I told you what radians per angle per unit time. What is that? I didn't tell you that we always, that our convention, the standard SI unit for degrees is, for angle, is not degrees, but rather radians. But that's it, baby. That's it. We do not measure, the standard is not to measure, final answers, blah, 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 are not turns, they're not cycles, they're not degrees. Our standard is to measure in radians. And then there's a very important and simple and profound relationship between frequency, cycles per second, and radians per cycle, and omega. Omega equals 2 pi f. If I give you f, thou shalt be able to convert to omega. If I give you f multiplied by 2 pi, because I'm turning from cycles into radians per cycle to get to radians. You must also know what a radian is. You must know that there are 2 pi of them to go all the way around a circle. More on that in a second. But here is one of the biggest equations here, the most useful equations here, V equals R omega. That gets us from angle land, or perhaps England, to velocity land. Or vice versa, if you divide both sides by R. You okay with this? So, let me put that on the slide, instead of just saying it verbally. Degrees suck. I mean, I have 3 degrees, but who cares about that? Degrees are not the system standard. What's a degree? Why divide by 360? Where did that come from? It's an easy thing to divide into chunks, but 360 is totes arbitrary. 2 pi is intrinsic to the nature of circles. If you divide, instead of one circle divided into 360 pieces, you divide it into 2 pi pieces, say 2 pi of these make up a full rotation. We get some very nice simple formulas that pop up later, as you'll see. Okay, now, if you need to do this for your homework and do not wish to think about the meaning of the radian every time, here is a conversion factor. 1 radian is roughly 57.3 degrees. That's 360 divided by 2 pi degrees per radian. Or you could also say that 1 full cycle, 1 full revolution is the same thing as 2 pi radians, sort of by definition. There is another more useful formula when you use radians, and that is that the length of an arc is mathematically called, you'll never believe this, the arc length. The length of some arc is equal, if you measure in radians, to r times theta. If you measure angle in radians, we get a very elegant, simple formula. How many meters long is this curve? Just multiply radius of the circle times the angle, interior angle of the circle. Hey, what is the interior angle if we go all the way around the circle? No, not 360. Give up your degrees. Give up your degrees. 2 pi. Radians. Forget degrees. Unless I give them to you in a problem and then convert immediately. Get radianed, man. The interior angle, if you go all the way around, is 2 pi. So what happens if we plug into this formula and find the arc length of all the way around? We get r times 2 pi rad. Wait, hold on a second. R times 2 pi. That's just the circumference formula. S equals r theta is nothing but some fraction of circumference equals r times some fraction of angle, where you measure angle in sensible units. What happens if I divide distance around a circle by time? What do you get when you get distance divided by time? What is distance over time? Speed. What happens if I have an angle divided by seconds? The angle divided by time. What's angle divided by time? What is the speed of the angle called? Angular speed, omega, right? So if I divide both sides of this equation by t, s over t is v, theta over t is omega. Oh my God, that's where v equals r omega comes from. You can look at this equation in more than one way. I've derived this in 2 different ways. How much do you want to bet this is coming up 5 times on your exam? These are very important ideas. You need to know what a radian is. If you have to look up 57.3, I won't be brokenhearted, but you need to know this arc length and its derived V equals R omega formula. Remember which side which goes on, okay? V equals R omega, S equals R theta, not theta equals RS, not omega equals VR, not V equals R over omega. V equals R times omega, S equals R times theta. I will be testing you on this. You should do it now. Okay? First, how much time do we got? We got time. We got plenty of time. Right? 15. I got you till 15. Okay, good. So what are we on? Google question D for delta is this. I want you to start by converting 7,200 rotations per minute. Here is rotations per minute into radians per second. And then tell me how long does it take to spin once? This is Google question E. Again, that's period. You know what you're doing? All you got to do, plug in and multiply and divide as appropriate. Ready, set, go. Again, tell me the angular speed in radians per second, our standard units now, and tell me the time, the period to go once round. Should round to 2 digits here, by the way, everywhere. 2 sig figs. A lot of correct answers. Turn to your neighbor and ask if you're confused. There are a lot of people who are slaying. Oh my God, slay, girlfriend. Anyone need the previous slide, by the way? Here, give you a minute on the previous slide. For part 2, I am not asking for, you should, for part 2, please apply reasoning to think about, 7,200 times per second around. Does it make sense that that would take 2 minutes to go once around? That should feel wrong. If something is going really fast, it shouldn't take a long time to go round. These are D and E. Please make sure you're putting them in the correct spots. I shouldn't have to say this. Okay, I'm gonna give it one more minute. Give me your best shot. Again, I strongly encourage you think about how long a second takes and think about how long it takes something that spins 7,200 times in 1 minute to do. If you're getting that it takes many minutes to make one full turn, I encourage you to talk to your neighbor because you done goofed, son. And time's up. Okay, so let's talk about conversions and how we do them here. Conversions and plugging numbers into equations. Let's do E first. What quantity am I talking about when I say how long does it take? This frequency, period, angular frequency, angle, you mama what? How long does something take? How long does one class take? Approximately 1 century, right? No. How long does one class take? What am I talking about? What term am I talking about? This is one period, right? I'm looking for period. If I say how long does it take to do something once, that's period. What do I tell you, by the way? I tell you rotations per minute. What's that? What does rotations per minute mean? What's a measure of? What is RPMs? Yeah, that's what it means, but like, what's it a measure of? It is a kind of angular speed, right? A frequency and angular speed. It's not measured in the correct units, radians per second. It's not measured in the correct units, rotations per second for either of those, but it's related to both of those. We can convert rotations per minute into what we need for finding period. The one and only equation that you've got for period is inverse frequency. So let's find frequency. It's the only way you know of to get period right now. So 7,200 rotations happen in 1 minute. And I want to find out how many rotations happen in one what? Second. So tell me, what do I do to get rid of minutes downstairs? What do I multiply by to get rid of minutes? 1 minute is the same thing as 60 seconds, right? Right? Okay, so if 1 minute is the same thing as 60 seconds, I can multiply by that. 1 minute cancels 1 minute. 7,200 divided by 60 tells me the rotations per second is, is that 120? Right, I did that right. Okay, so if I've got a frequency of 120 hertz, period is inverse frequency. Okay, please take a look back at this and reflect on how I'm getting this. Rotations, radians, degrees are all very common ways to describe turning. You need to be able to recognize the relationships between them. And hopefully, the relationship between 1 minute and 1 second, 60 seconds should be good. Okay, turn to your neighbor and discuss real briefly. How'd I get E here? Na, Kinder, frag mich etwas. Did it, da, did it? Pregúntamela. Ask me something. Sorry, I forgot which country I'm in. I forget everything. Yeah, yummy. Well, to be precise, how long questions? How long does? That's a time question. How long does it take to have a full class? How long does it have to take lunch? To spin once is saying that particular time for a full cycle. That's a period. The time for one cycle. Yeah? See in the words how it's identifying what? What I'm asking? Give me more! I hunger for your questions. I am a question pyre. Like a vampire, but for questions. Okay, so now that we've got F, what the F? 0.083, 0083. We can move on. If we've got F, we could find omega real darn fast. How do we get omega from F? How do we get omega if we got F? And how do we find our freaking Apple Pencil if we just had it? Anyone see the Apple Pencil I'm using around? There it is. Okay, so how I would do this, work it backwards to D, is to say omega equals 2 pi F, and radians per second. Oh my God, I could just plug in. Wait, hold on, that's period. 2 pi times inverse frequency. There's frequency. Whoops. 750 odd rad per sec. If you try to memorize this without meanings, just as alphabet soup, you're screwed. Thou shalt not treat this as a math class that you've done before where you memorize y2 minus y1 over x2 minus x1 is area, circumference, slope. Thou shalt, in physics, interpret the meaning of these things. We have talked about several measurements. We have talked about several concepts here. Let's review them real fast. Theta, what's theta? Angle. And connected to that concept, you need to know about degrees, radians, and turns, or cycles, or rotations, or revolutions. Okay? Omega, angular velocity. The meaning of angular velocity in terms of the definition in terms of change in angle per change in second. Thou shalt know the circumference formula. The arc length formula is a general case. And then you can plug in, if you forget, it's not 360R, 2 pi R. You got to use radians for that. Let me emphasize it like that. What's the other formula that we got? If you divide both sides by t, you get v equals r times omega. And what else? One more, period. And frequency. I am going, look, I am hoping that we have made some sense of this so that this is not something to be memorized, but to be reasoned about. But I will put on here, period equals inverse frequency, and therefore frequency equals inverse period. The relationship between those two quantities. That's everything we did, right? Yeah. That's a lot. But, and this is a big but, if you reflect on the meaning of these terms, it's really not that much. I'm going to introduce one more idea, which comes with an equation next time. I'm going to talk about centripetal acceleration. And that's, oh my God, 8 things that you need to know. Let me encourage you, as I said before, do not wait until the night before the final to try to put these puzzle pieces together. Think about the meanings, look for the connections, and this is way simpler than the alphabet soup that it would be if you just try to memorize these as letters. Take a look at this. Take a look at your notes. You have one, two, I think we have time for 2 questions. Please take a look and then ask me. I want 2 questions from the class. Or, wait, people are shy and don't like raising their hands. Put a question in. What are we on, G? We're on G or F? What the F? What the F? Put a question in what the F. Put what in the F? Ask me a question. Preferably about this material, not about my weekend. What the? And if you don't have a question, by the way, you don't have to write, I don't have a question. It is obvious to me that if you do not have a question. Okay, so good question here. How do I get 1 in this equation? Well, I think of it as the idea that cycles and seconds are related to each other. if I know the number of seconds and I know the number of cycles, I can combine these in two ways. If I know how many times something happens and I know how long it took for them to happen, I could take cycles over seconds, or I could take seconds over cycles. Either way, it's the same two ideas. Cycles over seconds defines frequency. Seconds divided by cycles defines period. Look, maybe the simplest way to say this is what would happen if you multiplied A over B times B over A? Cycles per second times seconds per cycle is 1. Multiplying a fraction by its reciprocal always gives you 1. So if you solve for one of those quantities, if ft means 1, then t equals 1 over f equals 1 over t. So that was to the answer to how do I get the 1 in the t equals 1 over f equation. Okay, what is s equals r times theta in the board? S equals r theta tells you the length of a fraction of a circle. This also tells you the circumference formula if you remember that angle is measured in radians and 2 pi radians is a full circle. R2 pi is the full circumference of a circle. If you were going around part of a circle, r theta gives you the fraction of that circumference, that part of the theta, that part of the 2 pi that you're going around. How do we get the v equals r omega? I take the previous equation. Here's the fastest way I know to do this, not period necessarily. V divided by any time. You could do the same thing to both sides of an equation, right? And then I interpret, what does distance around a circle divided by time around a circle tell you? Distance per time along any path is v, velocity. What does angle over time tell you? Angle, change in angle, per change in time is the meaning of omega. So I get v equals r times omega directly out of the previous equation. It's not really two equations, it's one equation and a division. When I mention rotation per time, it means the same as rev per time. Yes. Revolutions, rotations, turns, cycles, anything. When we solve for omega, what did you plug in for r? In the previous example, whoopsie. Crap. You can come up, no, because I erased this to write this. I needed a blank slide and I didn't have one. Hey, how would you all answer this? Because I forget what this is referring to. When I solved for omega, what did I use for r? I didn't have speed information here. I only had turns and time information. I didn't use the v equals r omega equation. I used the omega equals 2 pi f equation. Yeah. No, I think I just answered it to myself. Yeah. I didn't use v equals r omega. I don't have v. I don't have r. That's right. Period and frequency inverses? Yes. That's what I said. That's what he said. One last question. Is omega equal to radians per second? Omega is measured in radians per second. I would say x isn't equal to miles per hour. X is measured miles per hour, but yes. Great, we're out of here. See you Wednesday for one last thing about circles, and then on to elasticity.